Hello, welcome to another math video. Today we're going to solve a problem in this series of problems of this preparation process to IMC. So here it goes. This problem says prove that every positive integer n can be written as a sum of sums of this form: 2 to the ri, 3 to the si for Ri, Si non-negative integers, such that it doesn't exist a pair of distinct indices such that Ri is smaller than or equal to Rj, and same for the exponent s. So in other terms, we must have that no two summands here divide one another. So yeah, that's the basic idea. Yeah, in fact, the number k of summands here is also a variable, and here we can add for a k positive integer. Okay, so we have freedom also to choose k, not only the Ri and Si. Okay, so what's the idea to solve this problem? At first, the first remark that we can do is that if we have a solution for n, let's say we have something like this, then we can multiply this by any power of 2 and by any power of 3. We will also have a solution for n times this power. So we can say that n times 2 to the r, 3 to the s, it will be what the sum of 2 to the ri plus r, 3 to si plus s, and of course ri plus r smaller than rj plus I r, and same for s. This can only happen simultaneously if the same happened for the previous numbers here, which we know by construction that doesn't happen in fact. So here we are happy and we construct a solution for some number of this way. So what's nice is that we can really be concerned only in the case when n is coprime f6. So we reduce the problem to n coprime f6. Now the idea is to perform an induction. Okay, and what will be the idea of this induction? Okay, let's say that we have a solution for every k smaller than n, for every k smaller than n. Okay, by this observation here, we can suppose that n is coprime f6, because otherwise we could divide by 2 or by 3 and take the solution for n over 2 of n or n over 3 and then multiply it back by 2 or 3 to get a solution for n. So we can suppose this, and once we suppose this, we have in particular that n is not congruent to 0, 3, and so I can try to find some exponent p such that I can write n equals 2 to the p plus 3 times k. Okay. And in fact, what I'm trying to do here is to extract the greatest power of 2 that I can, and then after leave a number that's a multiple of 3. Of course, we have to see that 2 to the power of p is congruent to minus 1 to the power of p mod 3. So this is simply minus 1 if p is odd, or plus 1 if p is even. So since n is not 0, n is 1 or minus 1, and so we can find some p. And in fact, we'll consider the greatest exponent. So let p be the greatest exponent p prime, such that 3 divides n minus 2 to the p prime, and n minus 2 to the p prime is not negative. So we define p this way. Now we define k, which will be n minus 2 to the p over 3. So we have n equals 2 to the p plus 3k. And well, what's nice, we'll consider the solution for k. So that k will have some from I equal 1 to j to the ri, 3 to si. Okay. Let's take another. Okay. Perfect. We've done so. N equals 2 to the p plus 3k, and we are taking the solution here for k, which is sum for I equals 1 to g of 2 to the power of ri, 3 to the power of rj, no, of si, sorry. And once we've done that, we will have the for n, we'll have 2 to the pi, to the p, 3 to the exponent of 0 plus the sum here, and here I add 1 to this exponent. We know that no element of this form will divide this one, because here we have a factor 3, which we don't have here. So this doesn't divide this, and now we have to see the other way. So in other words, what we want is that the maximum of the ri's to be smaller than p. It's completely equivalent, right? Okay, since we want this maximum to be smaller than p, what are we going to do? Okay, by the maximality of p, we have to remember of this maximality. We know that 2 to the p plus 2, which has the same remainder modulo 3, must be greater than n. Okay. Which is 2 to the p plus 3k. So we have k smaller than, here is 4 times 2 to the p, so we have 3k smaller than 3 times 2 to the p, so we cancel the 3 and we get that. Since k is smaller, then every segment here must be also smaller, and so this is also true, and we've constructed a representation for by induction. Of course, we must not forget the base case, so for n equals 1 we simply have this. Right, maybe I'll just give an example to make it a bit more concrete. So let's say we're trying to represent I don't know, 20, 25. 25 would be too quick. 27. No, 27, 29. Okay. Have 29, which is coprime of 6. And so we see that this is going to minus 1, minus 3. Then, well, we must take an odd exponent, and we'll take the greatest one. Here it's greater than 29, so we're gonna take this one. So we're gonna write 29 equals 2 to the 3 plus 21, and here 21 is 3 times 7, and now we try to represent 7. 7 is 1 more 3. Just gonna write here 7 is going to 1 more 3, and so we must take an even exponent, and here we see that we must take 2 as the exponent. 7 is 2 to the power of 2 plus 3, and here we are fine because 3 is already in the representation that we want. So finally we go back and we simply substitute this representation here. Then we get 29 equals to the power of 3 plus 3 times 2 to the power of 2 plus 3. So finally this is 2 cubed plus 2 squared times 3 to the 1 plus 2 to the 0 times 3 squared. And here we are. Okay, so that's it. Thanks for seeing this video, and see you.